Well, hello there, ladies and gentlemen. Let's have a little look at compound and double angle formulae. Okay, very interesting topic and a vitally important topic for specialist maths. Now, compound first and then double angles second. We've got, with linear functions which pass through the origin, we know that f of a plus b equals f of a plus f of b. For example, if you had f of x equals 2x. Now, let's have a look at this. You know that f of 3 plus 4 would be f of 7, which would be 14, because f of x is 2 times 7, or 14. And you know that f of 3 plus f of 4 would be 6 plus 8, which would be 14, and they're both the same. So this is proving my point, ladies and gentlemen. For linear functions which pass through the origin, we know that the sums of the functions are, basically they work out. F of a plus b equals f of a plus f of b. Now, the plot thickens. With trigonometric functions, they are non-linear, and so we've got this problem here where we can't just go saying f of a plus b is equal to f of a plus f of b, as students might be tempted to do, because it doesn't work. For example, if y equals sine x, now we know that sine of 30 plus 60 would be the sine of 90, and sine of 90 is 1. But if you add them up individually, sine of 30 plus sine of 60, you'll get a half plus root 3 on 2, which comes to about 1.35, and it sure ain't equal to 1, guys. So this is the problem. So this is where we get the idea to come up with these compound angle formulas, okay? That doesn't equal 1, no. So that's why we need these funny formulas to work out this kind of thing of f of a plus b for trigonometric functions. That's why I did this little preamble over here. Now, here they are. Sine of a plus b equals sine a cos b plus cos a sine b. Sine of a minus b is sine a cos b minus cos a sine b. Cos of a plus b equals cos a cos b minus sine a sine b. Look, there's a lot of pattern in this. They're easy to remember once you get into the rhythm of them. Cos of a minus b is cos a cos b plus sine a sine b, and the tans. Tan of a plus b is quite different from the sines and the causes. It's tan a plus tan b over 1 minus tan a tan b. Notice how I've got the little pluses and minuses highlighted, because there's a real pattern to them. Tan of a minus b is tan a minus tan b over 1 plus tan a tan b. Notice the patterns to help your memory. I remember these. I know them off by heart. You could wake me up out of a deep sleep and I could just rattle them off. So you have to be the same. Notice here we've got sine cos and cos sine. Yes, that's what we've got. So that's the way these work. And these ones here, I've got cos cos and sine sine. There they are. So that's the cos ones, okay? Now, let's have a look at some examples here. We're going to evaluate sine of 7 pi on 12. Now, who knows what sine of 7 pi on 12 is? Well, I sure don't. But if we use compound angle formulae, we can do it. Because 7 pi on 12 is 4 pi on 12 plus 3 pi on 12. And we do know about 4 pi on 12, which happens to be pi on 3, and 3 pi on 12, which happens to be pi on 4. So, yes, that's right. So, therefore, we can say sine 7 pi on 12 is sine of pi on 3 plus pi on 4, and it's sine cos plus cos sine, and away we go. Plug and play, and hooray, we've got it. How easy is it? You see, it's rather marvellous, isn't it? A whole new branch of maths you just didn't even know about, just waiting for you to delight you at every turn. Now, we've got sine x equals minus 0.4. X is in which quadrant's that? That's 1, 2, 3, quadrant 3. That's right, sine's negative in that quadrant. Cos y is 0.2, and that's in the fourth quadrant, in which cos is positive. We have to find cos of x plus y. Now, using our double angle formulae, we can say that cos of x plus y is cos x plus cos y minus sin x sin y. Now, we haven't got cos x, we've got sin x. We've got sin x here, and we haven't got cos x, so we're going to have to find that. Now, over here, we do have cos y, that's the first term taken care of. Now, we've got sin x, but we don't have sin y, so we're going to work those out. And what we do for that is the marvellous patented Wolfie magic triangle. Actually, it isn't Wolfie's magic triangle, but I just call it the magic triangle. So if you've got, let's work this out now. We've got x over here, and we know that sine x is 2 over 5 or 0.4, even though it's negative. Don't worry about the negative for now. Just put the sides in here. That enables us to work out what the third side is by Pythagoras' theorem, which in this case is going to be root 21. But over here, dealing with the y, we've got cos y is 0.2 or 1 over 5. 1 over 5, and that gets us 25 minus 1 is 24. 24 is 4 sixths, so that's 2 root 6 from Pythagoras' theorem. And therefore this enables us to work out the missing links here, the cos x. So you can work that out now. Cos x is going to be root 21 over 5. And which quadrant was x in again? It was in quadrant 3. So that means that's going to be negative. And the other one was sine y we had to work out, wasn't it? Yes, sine y. So sine y is going to be 2 root 6 over 5. And this quadrant in quadrant 4 is going to be negative as well. So see, the magic triangle just fixes everything. Just fixes everything. So therefore that's right, and that's right. Yes, excellent. Now we can fill it all in and just work it out. There it is, cos of x plus y is that. And there it is, and Bob's your uncle again. Good old Uncle Bob. Okay, using CAS. Oh yes, this is, look, using CAS for this is too much trouble altogether. It's an absolute ridiculous farce. So have a look at this over the page. It's just madness. So you would do these by hand, right? This is a case where CAS just slows you up. Now, I know. Look, I'll just go through it step by step. Step 1, solve for the first angle. Now, what am I saying there? So you're solving for sine x is minus 2 over 5 for x, where with you've got the width symbol here, that little vertical line, where x is in that, between that, and you get that, right? Now, next step, you save the answer to memory. That's the angle that we got there, right? Third step, solve for the second angle, which is this thing here, right? Solve for cos x equals 1/5, wasn't it? That's right. Where you're in the fourth quadrant, you get this angle here over the page for more trauma. Now, this is step 4. You save the second angle, which we just found on the previous screen, to memory. By this stage, you've given up. It's ridiculous. Step 5, evaluate. Now, evaluate cos of a plus b, because you've just found a and b in the previous 4 steps. You do that, and you get this ridiculous thing here, which you think, well, you know, I mean, what the? And then what you have to do then is to use this little trick in the trigonometric menu on the calculator called T-expand, trig expand it is. So you just basically save the history of this down to here. We're inside the T-expand bracket, hit enter, and well, it finally gives up without a fight and you get it. But see, you just wouldn't do this on the calculator. It's just beyond ridiculous. Yes, that's what you do there. Step 6, use T-expand from algebra trigonometry menu. Okay, I just thought I'd show you that so you won't go using CAS for that sort of stuff. Double angle formula. These are rather fun. These are derived from compound angle formula. Yes, there's the compound angle formulae, I should say. And in all these formulae, because formula is a Latin word, if B equals A, then the compound angles above become 2A. That's right. And the formulae above become that. Yes, now we're going to simplify that a bit, and it looks even better. Simplifying, you get this. For sine 2A equals 2 sine A cos A. Cosine, cos 2A equals cos squared A minus sine squared A. Have a look, see if you agree. You do, don't you? And there's tan 2A is tan 2A today. Yes, it's 2 tan A over 1 minus tan squared A. That's right. Good. Now, lastly, but certainly not leastly, everybody, cos 2x can be expressed in 3 different ways, using sine squared x plus cos squared x equals 1 to eliminate either cos squared A, or sine squared A from the equation cos 2a as follows. Now, okay, that sounded like a lot of hot air, but look, here it comes here. There's your cos 2a equals cos squared A minus sine squared A. Now we're going to eliminate we're going to eliminate cos squared A because we're going to describe it as 1 minus sine squared A because sine squared plus cos squared equals 1. That's what I'm saying. So you rearrange that formula to get 1 minus sine squared A from cos squared A, and that way you can get this formula here without cos squared A in it if you don't want cos squared A in it. To that, cos 2A, second representation is 1 minus sine squared 1 minus 2 sine squared A. Now, or you can do the other thing and eliminate the sine. The sine squared A is 1 minus cos squared A, and you'll get that, which is 2 cos squared A minus 1. They're the three ways you can represent cos 2A. This one, the traditional one, then the first fiddle, that one, and then the second fiddling with it. That's the second way of doing it. Right now, this is summarising. There's a reason for that, guys. The reason that you represent these in this way and that way is because it's very important for using these formulae for anti-differentiation, which is coming up later in the course. So let's summarise these double angle formulae. Here they come. There, right there, and I've got the three different versions of cos 2A there. That one, and that one. Yes, good. Now, NB, this is what I was saying. These must, oh no, I wasn't saying that, but yes, you must thoroughly learn these. You must thoroughly learn them from memory. You must not rely on your cheat sheet because they need to be in your head so you recognise things when your eyeball hits the page and your brain starts working. Now, double angle is in the complete sense, yes. Double angle in the complete sense means that the pronumeral on the left-hand side of the equation is double that on the right-hand side. That's all it means. So if I had sine of 20x, that would just be double 10x. So the answer would be 2 sine 10x cos 10x. It's just double. It doesn't have to be sine 2x equals 2 sine x cos x. It can be sine anything equals 2 sine half of that cos half of that. Do you know what I mean? This has to be the double bit here. Double that and double that. Yes? Same thing with cos. That's right. Now, what did I say here? Equations 2 and 3. Oh, yes. Equations 2 and 3 above are necessary for anti-differentiation later in the course. Okay, so that's what I was saying just before. Now, which is in a future topic. Yes. And they become this, you morph them into this form here, and they're very, very useful for anti-differentiation. In fact, they're essential for anti-differentiation. So they need to be thoroughly learned and understood. Now, here's an example for you. Now we're getting into examples. If sine x equals 0.4 and x is in which quadrant? Quadrant 2. Find sine 2x. Well, we could do that if we could find cos x, because sine of 2x equals 2 sine x cos x, so we have to use the magic triangle, I think. Yes, we do. We do. Here comes the magic triangle. Now, sine x equals 0.4, let's put it in. That's 0.4 would be 2 over 5, wouldn't it? So we'll just do that, and then we'll find by Pythagoras' theorem that the third side here would be the square root of 25 minus 4, which would be root 21, I would think. Oh, yes, it is. There we go. So therefore we know what cos of, yes, sine x was what? Sine x was 0.4, therefore cos x is going to be root 21 over 5, but is it going to be positive or negative, ladies and gentlemen? Well, in this quadrant here, it's going to be negative, okay? It's going to be negative. So, yes, very good. So there it is. Cos of x must be minus root 21 over 5. Now we can fill it all in the gaps and we can do our formula here. Sine 2x is 2. Sine x cos x. There's the sine x. There's the cos x. Bob's your uncle again. Hello, Uncle Bob. That's the answer. Now, what's this? We're doing beta now. If cos beta is 0.6 and beta is in the fourth quadrant, find sine of beta on 2. Okay, it looks like a case for double angle formulae, doesn't it? Well, therefore, let's go with this. Now, if beta is between 3 pi on 2 and 2 pi, I think we need to know what beta on 2 is between. Yes, 3 pi on 4 and pi, just halving each of those numbers. So that tells me what quadrant is beta on 2 in. Therefore, 3/4 of pi to pi, that's quadrant 2, somewhere in the second half of quadrant 2. That's right, isn't it? Yes, yes. Okay, that's pretty important. Now, so to get that, we've got to use a double angle formula. We're required to get sine beta on 2. I think we've got to use, I know what we've got to use. Yeah, where are we? Beta on 2, yes, yes, I got all that out. So therefore, sine of beta on 2 is going to be positive. And this is the one I was trying to think of. Cos of beta is 1 minus 2 sine squared beta on 2. Now, this is the one we've got to solve for here, sine of beta on 2. We know it's going to be positive. So and we know what cos of beta is. It's 0.6, isn't it? So we just got to solve it now. It's easy. Here we go. So therefore, yes, 0.6 is 3/5, so therefore that's our little equation which we're going to solve for sine of beta on 2 for. And yes, that's right. Next line, that's right. And therefore it looks like sine of beta on 2 according to that would be plus or minus 1 over root 5. But we know from our analysis up here that it's going to be positive, so we're going to reject the negative solution. It's positive, and therefore sine beta on 2 is 1 over root 5. Oh, that was the end of our video. Wasn't that fun? And time really flew there for that video. So it's simple stuff. You just have to remember the formulas and keep your head together, and you'll be absolutely fine with this stuff. Okay, and we'll see you in the next exciting video. Bye for now.